installment in my Cura 2.1 tutorial series. This is the second part of the advanced settings, and just a quick recap. The very first video talked about setting up a new machine in Cura. Now, as of this recording, Cura 2.3 is in beta, and that will allow for much simpler machine addition. But for now, if you don't want to use the beta and you want to use the stable, you'll want to watch that first video to get a machine set up that isn't already integrated into Cura 2.1. Then the next video, we talked about basic settings and sort of the quick start tutorial that would get you printing even if the settings weren't necessarily perfect. And then in the video previous to this, we began with a more advanced methodical approach of stepping through each category and talking about every single setting as we went. So that's where we left off, and we're going to be starting off today with the material category, looking at all the settings here, and then moving on down the list. We'll see how far we get. We may be able to finish it off, or we may end up running out of time and needing to do a third advanced tutorial. So let's get started. Alright, so the material category is critical. It has some of the settings that will be the most important to the print quality and print success out of just about any of these categories. So starting off here, we've got printing temperature. This is of course going to be material specific, but more than just being material specific, it's also going to be machine specific. The thermistor that's in your hot end, or the thermocouple, depending on what kind of machine you have. Its calibration and its point of reference will be different than the next guy's printer. And in some cases, even if the guy next to you has what's supposed to be the same printer, there can be some differences. So the temperature that you print at is critical in the sense that each material that you may choose to print is going to have a different optimal temperature. But even if you have a specific material and guy A over on some forum says print at 205 degrees, well, you may find that for your printer you need to print at 200, you need to print at 210. And the other thing that impacts it is the size of your nozzle and the speed that you're printing at. For example, if you're printing with a large diameter nozzle and a tall layer height, the volumetric flow rate through your hot end is going to be high. And what that means is that the plastic coming into your nozzle has less time to melt and reach the desired extrusion temperature, and so it means you may need to print at a higher temperature if you're printing in that manner. And then on the flip side, if you're printing with an ultra low layer height, maybe 100 microns or even 50 microns, and you're printing slower, maybe you're doing a very highly detailed print, the amount of plastic moving through the nozzle volumetrically is now very low, and you're probably going to want to print at a much lower temperature. So the print temperature is a very flexible number. It's what would be called a process variable, and its value will absolutely change depending on the kind of material you're using, the speed that you're printing at, the layer height that you're printing at, and the manufacturer of the material. So for example, if you're printing with PLA and you have 3 different manufacturers, almost guarantee that each one of those manufacturers' version is going to have a different optimal print temperature. Now there's absolutely some ranges for each kind of material that it should print fairly well in. For example, PLA typically between 190 and 210, ABS typically between 220 and 240, or maybe 230 and 250. PETG actually has a very wide processing envelope. It can be anywhere from 220 up to 260. So there are ranges, but you absolutely don't want to rely on somebody else's experience or even the recommended temperature range for your printer, simply because the material is really what decides what you need to print at, not the machine. And most manufacturers will give you a very wide range because they already know that the optimal temperature could be anywhere for a specific machine, and they don't know, so they're just going to give you a super wide temperature range. It doesn't mean that you should print over that whole temperature range. It simply means that your number for best success with your printer will probably lie somewhere in there. Okay, that was pretty long, but it's very important to understand that print temperature is not set in stone, and it's something you need to determine for your own printer and the materials that you tend to use. And it's something you're going to do through experimentation by using simple test objects like this cube, and maybe slightly more advanced test objects like the Benchy 3D boat benchmark print. You can search Thingiverse if you're not familiar with it. But it's also very important. Wrong temperature can make a printer look terrible. The right temperature can make even a cheap printer look like a rock star. Alright, moving on, bed temperature. This is pretty straightforward. Bed temperature is typically used to alleviate warping in materials, and it's a much less critical value. Typically, materials that like to warp are going to be printed at a much higher temp. For example, ABS, somewhere between 80 and 110 Celsius. PETG, somewhere between 50 and 70. PLA doesn't need it necessarily, although for long, thin, or wide PLA parts, having some heated bed temperature, maybe 50 to 65, can be helpful as well. So that's something that you'll just be tweaking based on what your material is and what you're printing on. For example, if you're printing on glass with glue stick, or you're printing on blue tape with glue, or a PEI sheet, all of those have different temperatures and material combinations that work well, and that's something where you can typically get a pretty good guesstimate off of other people's experience. And if somebody says, yeah, I'm printing with X material and my bed temp is this and I'm not getting any warping, you can probably lean on that number pretty well. But again, it's another thing where experimentation for your specific printer is what's going to be most critical to your success. Diameter. This is the filament diameter that you're using, and the industry standards are 1.75 and 3, and you'll only be using 1. So once you know what your printer has, set it and forget it. Flow. This is something we can use to modify the volumetric flow rate depending on several things. So what it's saying is that if the number of revolutions that your extruder turns to move a certain volumetric section of filament, if we go higher than 100%, it's now going to rotate that percent more every time we tell it to move a certain distance, and it will extrude that much more. Or vice versa, we can go below 100% and it will actually turn slightly less for every unit of material that we tell it to extrude. And this can be useful for tuning in a specific material that maybe the manufacturing tolerances are slightly out, or more often than not, it's simply based on the way that the material flows. Some materials, they just print cleaner, slightly under extruded. Some materials print a little stronger if you slightly over extrude them. It's probably not the first value that I would start playing with under the material preferences, but if you see a print that's looking very kind of bloated, or there's just always extra material that seems to be getting picked up by your nozzle, and it just looks like it's running into plastic all the time, dialing in a little bit of under extrusion might help clean that up. I had a roll of PETG once that was actually a carbon fiber filled PETG, and it needed to be run at 90% flow rate. 100%, it just made a massive mess. 90%, it was perfect. The parts were strong, they looked clean, and that was just the flow rate that it needed. And part of that has to do with volumetric expansion, and part of it had to do with the fact that the material was so hard that my extruder gears didn't actually sink into it enough, and I was actually over extruding because it was riding on the outer diameter of my extruder wheel rather than the inner diameter. Alright, retraction. Retraction is probably something that I would nickname the printer killer. It is very important for good print quality, but it's also one of the things that can cause jams. It can mess up hot ends, and can generally just be a massive headache. So to demonstrate this, I'm going to move over to another window where I've got a little render of a hot end, and we can just quick go over what retraction is and hopefully dispel a couple myths about retraction and think about it visually, and I hope this will be helpful. So here's a quick mock-up of a hot end. Anybody with a monoprice Select Mini will recognize this immediately. This is the design of the stock hot end for that printer. This clear or see-through section is actually an aluminum heatsink that a heat break gets clamped to with a set screw, and then you've got your heater block, and you've got your nozzle, and in the stock configuration, this little white strip is a Teflon liner inside of the heat break that reduces friction and reduces heat transfer as well from the heat break to the material. Now, the concept behind retraction is that once the filament has reached the tip of your nozzle and you're actually extruding plastic out of the tip, anytime you want to move through space without extruding, if you don't do a retraction, plastic will continue to ooze and drip out of the nozzle, and it can create strings and blobs and artifacts on your print. So if you pull the filament back up out of the nozzle, you can take pressure off the tip of the nozzle, and this is the first myth that we need to dispel. Some people believe that when you do a retraction, it actually pulls all of the plastic out of the nozzle, kind of like this little demonstration here would indicate. However, that's not the case. The plastic that's at the tip of the nozzle when you begin the retraction is still melted, it's still a liquid, and actually not just the tip, but actually a good ways up the nozzle, it's all going to be liquid. And you can't just pull that liquid out with the hardened filament. It's going to stay in the nozzle, so what's going to happen is that you're going to do the retraction, the hard filament up here that hasn't melted yet, all the way down into the transition zone, into some of the softer filament that's still connected to the hard filament but has started to melt, is going to get pulled up. And what you're going to do is you're going to relieve pressure on this portion of the hot end where the plastic is liquid. And relieving that pressure will immediately prevent fast oozing from occurring. Now, depending on the plastic you're using and the temperature you're printing at, the liquid plastic might still ooze of its own accord out of the nozzle tip for two reasons. One, it's in the liquid phase, and just gravity will allow it to ooze out of the tip. And two, if you've been printing relatively quickly, that is still heating up. It's actually probably still heating up to the actual temperature of your heater block, which means that volumetric expansion is occurring. And volumetric expansion happens when that plastic heats up. Different plastics have different coefficients of expansion, and unfortunately, materials like PLA, which are really common, have a very high coefficient of thermal expansion. And so, even after you've done that retraction, you might still see oozing in some cases if you've been printing fast, because that material is still heating up and it's still expanding out of the nozzle tip. Now, people who have Bowden tube printers, and a Bowden tube is where there's a feed tube from an external extruder that's not mounted on the print head that feeds the filament to the hot end, will often end up using much higher retraction values than people with printers that have a direct drive setup where the extruder motor and extruder are right on the print head. There's no long tube connecting them. The filament gets fed into the motor, pulled through the extruder, and pushed directly into the hot end. Now, most of the time with direct drive printers, you only need maybe 1 to 2 millimeters of retraction in order to reduce the pressure in the nozzle enough for your move to be clean and not have any stringing. Now, in Bowden setups, you don't need lots of retraction because you need to pull the plastic all the way out of the nozzle. You need lots of retraction because there's slack in your extrusion system. If you've got a Bowden tube that's connected here, and then it goes all the way over to a printer extruder somewhere off on the side, you have all this Teflon tube which has an inner diameter larger than your filament diameter. And what that means is that there's slack, there's some backlash in there. So the large amount of retraction that you're specifying is simply taking the slack back out of the tube. And then at the very end, that last millimeter or so is where it's actually pulling filament out of the hot end. Everything before that is simply taking slack out of the system. If you want a good demonstration of this, you can turn your hot end on, prime some filament, so you know it's all the way into the nozzle, turn it off and let it fully cool. Then, if you've got an extruder that has a lever on it that you can use to disengage the idler gear, you can grab your filament and push it and pull it, and you'll find that even though it's stuck in the nozzle because it's hardened, you're going to feel a significant amount of play on a Bowden setup, and that is what most of your retraction's doing. It's actually just taking up that play, and then the very last little bit of it is what's actually pulling out the filament. So the large variance in retraction settings between direct drive setups and Bowden setups doesn't really have anything to do with the difference right here in the heater block. The exact same behavior is occurring. It really has everything to do with the difference in the mechanical nature of a Bowden versus a direct drive setup. And you will also see in some cases that the Bowden tube can act a little bit like a spring, especially with long Bowden tube setups with really long feed tubes, and that can cause some other interesting behaviors in the accuracy of your extruding or your extrusion. I'm not going to go into that too much. That's more of a printer-specific behavior, and it's difficult to talk about that with clarity in a more generic sense. But retraction is the same for everything. It's simply relieving pressure in the nozzle by pulling filament out of the very tip of the nozzle and allowing the pressure in there to very quickly equalize. Now, a couple dangers with retraction as it relates to clogging. If you have a heat break, which is this yellow part, with a Teflon liner, which is this white part, and you have too high of a retraction setting on, and you're actually pulling your melted filament out into the Teflon liner, you're going to begin to break down that Teflon liner much sooner in the best case, and in the worst case, you'll be seeing clogging almost constantly as you get melted plastic pulled up into the Teflon liner. It's okay if the material is soft, even very soft, in the Teflon liner, but what you don't want to have happen is you don't want liquid plastic getting pulled all the way up into the Teflon liner. So that's one place where really high retraction settings can be damaging to your printer mechanism. We're going to switch back to Cura now as we get into some of the more nitty-gritties. So we talked about retraction distance a bunch, and this is something where probably the best way to figure out what your retraction should be, if you don't have a very reliable manufacturer value for it, is to take some of these test cubes, make a copy, maybe just 2 or maybe even 3, space them out on your build plate as far as they can go, and then start at a relatively low retraction value and run a test print. If you have a lot of stringing, start increasing your retraction distance probably 0.5 millimeter at a time until you are seeing a reduction in strings or a complete elimination of strings, ideally. So retraction speed, and these are 2 great settings that are available in Cura 2.1, is both the retract speed and what they call the prime speed. And this is basically just talking about both directions of retraction. So the retract speed is the act of actually pulling it out of the nozzle, relieving that nozzle pressure, and the prime speed is the act of moving it back into the print position. Now, the retraction portion is where we're actually relieving that pressure, and the faster we can do that, the better, because it will absolutely minimize our potential for oozing as we're doing a fast move from one part of the print to the other. So I might want to set this at maybe 60 millimeters a second. Now the prime speed isn't as critical because we're simply returning the filament to the nozzle, and it's not going to start extruding until the prime is completed. And because we've pulled that filament out of the nozzle, it's possible that in the amount of time that it took for it to move, it's actually started to harden a little bit if it was soft at the tip, which was going to cause a little more friction on the return travel. So slowing that down a little bit to give the stepper motor and the extruder gear a chance to grip the filament fully while it's returning it can prevent grinding, where the extruder gear slips on the filament and starts to grind a little divot into it which can be dangerous for a couple reasons. One, if it does that too often, it'll actually just cut a chunk out of the filament and it'll stop extruding, and you'll have to restart the print. You'll come back and you'll see it just moving around in midair with nothing coming out of the nozzle. And then the other thing that is actually a little bit harder to detect is if the gear is slipping on the filament and it's not jamming and it's not stopping printing, but the motor is moving the full amount that it should. For example, if the retraction is sent to 3.5 millimeters and it goes to do a return prime and the gear starts to slip, the system thinks that it's returned the filament 3.5 millimeters into the nozzle, but it's possible that for maybe a millimeter of that distance it was slipping on the filament. So now it's only moved it back 2.5 millimeters. It's going to begin printing, and you're going to have under extrusion. You're going to have lines where there's no plastic extruded in your print. It'll make it weak and, of course, ugly. So we don't want to run into a scenario with our retraction and prime speed where either value is so high that the extruder gear begins to slip on the filament and it loses track of how much filament it's actually retracted or primed. Another scenario that can actually make a print look really messy and globby is where the retraction slips and the prime doesn't slip. So it thinks it's retracted it out 3.5 millimeters, but maybe it slipped for 1 millimeter of that retraction, so it's only pulled it out 2.5. And then the prime doesn't slip and actually pushes 3.5 millimeters of filament back forward into the nozzle. Well, now since it actually only came out 2.5, we just extruded a full millimeter of plastic into our print and created a big glob on the outside, or perhaps a big area of stringing. So we never want our retraction speeds to be so high that the extruder slips in either direction. Now, if that's happening a lot, even at lower speeds, it probably means that there's an issue with your extruder. It's possible that the spring isn't strong enough. It's possible that there's a portion of it that maybe has a crack in it that's making it not apply enough tension to your filament. So you want to have a good extruder for this. Well-designed machines will be set up and designed in such a way that this is never an issue. If it's a cheaper machine or maybe something that you printed yourself as a replacement, you might have to take a closer look at it. And of course, you can go too far. If you have a really tightly tensioned extruder, you can actually begin to flatten the filament, which can have a whole host of bad side effects, including things like getting jammed because now the filament's very wide and it's getting stuck in your Teflon tube. It can also result in under extrusion because the flat filament is now thinner than it should be, and it's not actually pushing the right amount of filament through. It's actually under extruding because it's rotating on a smaller diameter cross section. So retraction is really critical, the speed's critical, and your extruder, which is the hardware part of it, all has to play very nicely in order for clean, functional retraction to occur. Retraction extra prime amount. This should never be used. The only time you would use this is if you are actually consistently losing material during moves because it's oozing out, which, unless you're printing with a really strange material that you literally cannot eliminate oozing from, and you know you have to replace it with a little extra filament at the beginning of each move, it's really not recommended to use extra prime. Most of the time, for most people, with most printers printing with most materials, if you feel like you need to use extra prime, it's because there's something wrong with your extruder and retraction settings, and if you fix that, then the extra prime amount won't be necessary. So this should be a last resort, or only in scenarios where you absolutely know you can quantify that you're losing plastic during certain moves because of dripping that you can't control via any other method, and then you have to replace a little bit of that lost material. One example I can think of right off the top of my head, I guess, for extra prime would be if you're printing with a flexible material and your extruder setup isn't robust enough to handle retractions for flexible materials, and so you drip a little bit out every time you move, then you'd want to have a tiny bit of extra prime amount to replace that oozed out flexible filament when it begins extruding again. But that can also be remedied by putting in a better extruder or modifying it to handle flexible filament better. All right, so the next three have to do with how often it can do retractions. And all three of these parameters basically attempt to prevent excessive retractions in a small amount of either physical distance of the nozzle or physical length of filament. So you don't want many retractions happening on a very tiny piece of filament, because it'll start to grind into that filament, it'll start to flatten it out and wear it out. And so these three parameters attempt to control that. So the first one just says retraction minimum travel. This one's very simple. If the nozzle hasn't moved 1.5 millimeters since the last retraction, it won't retract again, even if it would under another circumstance. I actually think 1.5 is a bit high. However, it can speed up your prints whenever it's doing infill or solid moves up against an angle where the next line over it actually has to move at an angle. And if you have this number too low, it'll retract every time it switches those lines, which can add a lot of time. And it really depends. If you're printing a very small model with a detailed pattern, you may find that you need to turn this way down, otherwise it won't retract, and it'll wipe plastic across that pattern, kind of smearing it over. On the other hand, if you're printing larger items where you don't have that kind of detail concern, turning this number up can be useful, because it might decrease your print time without really any noticeable quality change. So this one is something you can play around with, but 1.5 millimeters is probably a happy medium for most prints. So these two values go together. Basically what it's saying is that if within 3.5 millimeters of extrusion, it can't retract more than 90 times. So, and if you had a print where it was trying to retract more than 90 times and 3.5 millimeters of extrusion, it would have to be a very complex part and would probably require some other tuning as well. So these numbers are pretty much safe values that you can use for most prints. And then the final item under material is Zhop when retracting. And the idea behind this is that as soon as it retracts and it goes to do a high-speed move, it's actually going to raise the nozzle or drop the build plate, depending on what type of printer you have. So there's a little bit of a gap between the layer it was just printing and the nozzle as it moves. And the biggest benefit to this is that if there's a little bit of curling on your print where an edge is curling up, or there's some little defect or surface blob, the nozzle won't hit it as it's traveling. And if it's doing a high-speed travel, it alleviates the risk of either knocking the part off the bed because the nozzle hits it, or the nozzle hitting it and actually causing the stepper motors to skip and lose their place with respect to the home position. Typically, you can leave this at 0. There are some printers, like Delta printers, where Zhop is more useful, or on printers where you have really high travel speeds and you're just concerned about a small collision point causing a problem. And in those cases, the Zhop really shouldn't need to be more than the distance of one layer height. So if you're printing at 200 microns, a 200 micron Zhop should be sufficient. And in some cases, even less than that's fine, maybe even 100 microns. So just be aware that if you're using a printer with a threaded rod for the Z motion, Zhop will add a lot of time to your print, or can add a lot of time to your print. If you're using a system that uses belts to drive the Z, or lead screws, those Zhop moves can be made pretty quickly, and it probably won't add a lot of time to your print. Okay, we got through material. That's a huge category, a lot of important parameters in there.